Hi, this is a bit of asynchronous presentation. We're going to continue the discussion of rotations, but I want to talk briefly as a kind of a side point about the rotational inertia. Rotational inertia, which is sometimes in the textbook simply called the moment of inertia. That's a historical mathematical term. I want to basically do two things. I want to define it so you can figure out where it comes from. And I want to show you how it's calculated. But as I mentioned in class yesterday, I guess it'd be, I'm not expecting you to actually do these calculations. I just want you to see, and so that you know where these things come from, so that if I ask you a conceptual question, you'll have a handle on what to expect. So the moment of inertia, I, for a continuous body, a body that has material in a rigid form that's distributed over some region, is defined as an integral, and it's an integral over all space. So it's one of these annoying three-dimensional integrals of a quantity which I'm going to call R, and I'm going to label that R with the little serif here so that I distinguish it from my usual R, squared df. So we have to unpack that integral and figure out what it means. So when I say R, so again, I'm going to draw a generic object corresponding to, say, a potato or something. There's my potato. And that if I have an axis to that object, so I will define the axis as a kind of if I spear it with spear the potato with a skewer, something like that. So this corresponds to an axis going through the potato, coming out the other side, sort of stuck at some arbitrary location. Then if I consider a little bit of material in that potato, so here's a little bit of material. I'm going to define that little bit of material as like a little cube of material with some volume. So this little material is a little bit, that's what I mean by dm. It's basically a little piece of matter that's sort of sitting there. And then for that piece of matter, any piece of matter I pick on this arrangement, I define the quantity R as the distance from that piece of matter perpendicular, so that's the key issue, it's perpendicular, from that radius to that location. So let me highlight that in yellow so we can sort of focus in on that. So that's what I mean by the vector serif R, not squared, just R. And if I take that length squared and I multiply it by this mass dm, and then I integrate over all the masses, that's what I mean for that moment of inertia. And notice something important, that this moment of inertia is defined relative to not only this object that I'm integrating on, but it's also defined relative to the axis. The definition of I, unlike mass doesn't care about the coordinate system. If something's 5 kilograms, it's always 5 kilograms, no matter where you put your coordinate system down. But if I choose the location change the location of the rotational axis, I will change the moment of inertia. Okay? So let's look at some examples of symmetric objects where we can actually apply this to. And I'll actually start with the simplest one. So an example is a thin hoop. So I mean, what do I mean by a thin hoop? I just mean like a ring of material where the dimensions, the thickness of the ring is quite small compared to any other dimension. So a narrow wire, a rigid wire of material, or, it could also be a hollow cylinder. It could be anything that basically is described by this description where it's empty here and empty here, and all the materials basically in this narrow range. And for this hoop, I'll define the radius r and the mass will be m. So those are all given. And so I want to basically calculate the center of mass. And the usual thing we will do is we will determine the center of mass relative to an axle that goes through the center of mass of the system. Now, it's interesting because this axle actually goes through empty space. So it's a rotation about that empty point, but it's still, that's the center of mass point. So we can basically write down the calculation. I, for a hoop, and implicit here is about the center of mass, is equal to the integral of, again, that quantity r squared dm. But in this case, I'm doing this integral over all space. And what that means is that when I do the integral, any place where there's matter, I'm doing the integral, but any place where there's no matter, in other words, empty space out here and in here, but at that part of the integral will contribute nothing. In fact, all of the little bits of matter, so here's, for example, a tiny little bit of matter on that hoop, are all at the same radius where from that axis, which is the radius r of the hoop. So in other words, r squared here, when I integrate over space, the only place where I get matter is at the constant distance r. So this just becomes equal to, well, r squared is a constant, which I'm going to set to big R. And then once it's a constant, of course, integrating a constant, I can pull the constant out. So this just becomes r squared times the integral of dm. And again, I'm integrating all the little bits of matter over all space. So anytime I do an integral of d anything, it's just the total of all that thing. In other words, this just becomes, this is just this quantity here. That's just the mass of the hoop. So that means that this is just equal to m r squared. So the rotational moment of inertia, the rotational inertia of a hoop about its center of mass is mr squared. And we integrated, but it was an easy integration because we didn't actually have to take any antiderivatives. We literally just noticed that that's constant. Okay. Let's do one that's just a little more complicated. We will erase here. And erase here. So now we will do what is a thin disk? A thin disk. So what do I mean by a thin disk? So what I mean by a thin disk is an object like a penny or something that the extent of the disk is the disk is solid. No, it's not like the hoop, it's filled in. But it has some, arbitrary but unknown thickness, right? So it's, so it's basically, what are the parameters? There's a parameter m, which corresponds to its mass. There's a parameter r, corresponding to the distance. And then there's a parameter t, which I will label, let's just call it, again, a funny letter t corresponding to the thickness of the disk. Right, which is a quantity that turns out doesn't come into the calculation directly, but we have to contend with. Why do we have to contend with it? Because in order for me to do the integral, again, I'm going to take a little piece of this material. So there's a little piece of the material right there. I need to consider, in order for me to work out what dm is, right, I have to basically have an expression for calculating dm, right? So one way of thinking what dm is that's just the mass. Well, the smaller this volume, the smaller that mass. And the proportionality between mass and volume is what we call density. So I will distinguish this. So let's write this down. If I say mass density, and I will usually use the Greek letter rho to talk about mass density. Mass density is defined as simply the total mass over the total volume of any given system. So if I have a fixed I have a thin disk of uniform density, I just have to write down those expressions. Well, in this case, that's just equal to the mass, which is a given, divided by the volume of this penny. Well, the volume of the penny is just of the disk. It's just the surface area of the disk times the thickness. So in other words, the surface area of the disk is just pi r squared times the thickness, which again, I'll label by that funny letter T there. Okay, so this is my definition of rho. And once I've got that, then I can say that dm is just equal to the little bit of material is just equal to, so in other words, to get from density to mass, I multiply by volume. So m is just equal to the density, which I've written down here, times dV. And again, I'll put a little surface up there to emphasize that this is essentially the differential volume. And in this case, the question is, how do I pick a differential volume? I wrote a little square here, but the problem with the little square here is if I don't have an easy way of like moving two-dimensionally across that surface if I'm using little squares or little cubes. So I use the cube to give the idea of a little bit of volume, but the real volume I want to use is, instead of a little cube, little square, I want to use a little annulus. This is the usual trick we do in calculus, is that we do our integration in a way that has a symmetry that matches the object in question. So let me draw the disk one more time. That's the disk itself. I'm going to make it nice and big. That's the center point there. And then when I do an integration, I'm going to define the dm to be the mass associated with a small annulus. There's my small annulus of some particular thickness, where that thickness there corresponds to dr. And then, of course, I can ask, well, what is the volume of material that is basically incorporated around that little bit? So in other words, dm is just equal to rho times the volume of material in the annulus. Well, the volume of material in the annulus is approximately the limit that dr gets small, the circumference, that coordinate, times that width, times that thickness. So again, that's just equal to 2 pi times r, where r is the distance that I'm doing the integration out to. So 2 pi r, so this is all dv, 2 pi r times the thickness, again, t times dr. Okay, that whole thing is dv. That's the tricky part of doing this, is to convert dm into something where I've got a dr. So the happy news is, once I've done that, then I just have an integral, and the key issue is that I'm integrating these annuli from 0 out to capital R. So let me just write out the integral now. It's not hard calculus, but again, I'm showing you it. I'm not expecting you to do it, but just so you know where it comes from. So so we basically say, okay, the moment of inertia is equal to, again, here, this will be r, which is the distance out from there, squared, dm, where I'm integrating r from 0 to capital R, okay? And again, this is now equal to, we'll use this expression here, so this is now equal to the integral of r squared times rho, which we have an expression for here, times 2 pi r times the thickness, tau, t rather, funny t, times dr. Okay, so it's a little bit of a mess, but the happy news is we can bring all some things out. Almost everything here is a constant, except for the r's. So we get on the outside, we get a rho. Well, here, actually, I'm going to take the rho outside, and I'm going to write down everything we know. So what goes outside? So I'm going to take that expression. So rho, which is m over pi r squared t for the thickness, that times, I'm going to bring outside out here now a 2 pi, because that comes out, and another thickness, and then I'm going to do the integral, which is going to go from 0 to r of r to the third dr. Okay, so that's an integral we can do, and we notice some things right off the bat. What do we notice? We notice, well, here, let's just carry on over here. So I'm going to erase this so that I can keep doing the calculations. But remember, this is our definition of mass density, mass over volume. That's the key idea. So I'm just going to keep doing the algebra just to get to the answer, so I can basically make my last point. Okay. So what do we know? The pi's cancel. Well, let's see. The t's cancel. So this is equal to m here over r squared times 2. So there's a 2 left over here. And the integral of r cubed is r cubed. The antiderivative of r to the third is r to the fourth. But I'm going from 0 to r, so this just becomes r to the fourth over 4. So that just becomes, oh, look, those cancel out, that cancels out, and I end up with 1/2 r squared. Again, this is for a disk, which is the same as a massive pulley, basically. That's what a massive pulley is. It's a disk with an arbitrary thickness. Notice the thickness doesn't come into the calculation. So again, it's simple calculus, and in principle, it's something I could ask you to do. But for the summer class, I don't bother. It's not worth it. But I do want you to notice something about the bottom line here. So the bottom line is that for a disk, for hoop, I had mr squared. So let's write down the answers that we have so far. Okay. Again, this is all about the center of mass. ICM for hoop is equal to mr squared. ICM for a disk or pulley is equal to 1/2 mr squared. In other words, it's less. And the reason it's less is because for the same mass and the same radius, remember that definition of the integral. The integral is 1 over r squared dm. So for the same mass, there's more mass closer in a disk than there is in a hoop. All the mass in a hoop is at that distance r. Whereas for a disk, there's a lot of material that's closer. So I end up with a smaller number because I get a smaller average value of r here. Okay. You can do the same techniques. It's more complicated because you have to deal with 3-dimensional limits, so you can't just use an annulus. But nonetheless, it's still standard calculus to get the moment of inertia, the rotational inertia for a solid sphere. And when you do all the calculus correctly, you end up with the answer that is a 2/5. What a weird thing. 2/5 mr squared. In other words, there's always something times mr squared where this factor is smaller if there's more material concentrated towards the axis. Okay. In contrast, I for a hollow sphere, so this would be for a shell of material that's empty with all material on the outside edge, this ends up being 2/3 mr squared. So not as much as a hoop, but more than a disk. There's 2 other shapes there's 2 other results that you want to know. I for about the center of mass for a thin rod is equal to, well, it turns out you do the calculus, this rod has very little stuff outside, almost all of the stuff inside. You get a very small number, 1/12 m times, I'll write this as a little script L squared, where L is the length of that wire, of that rod. But often we don't want to rotate about the center. We want to rotate about one end. So about an end of the rod, well, now there's more material towards the outside. That's 1/3 ml squared. Okay, so these results for hoop, for disk, for solid sphere, and for hollow sphere, and also for a rod about the center of mass, and for the rod about one end. I won't ask you to derive these, but I will ask you for not this week's exam, but for the final exam, to have them in your pocket. When I say hand them in the pocket, what I mean is that they'd be written down on my review sheet, and you should copy them to your crib sheet so that you know what these are depending on which shape you have. Again, notice the more the material is outside, the more expanded the object is, the bigger the rotational inertia for the same mass radius. The more compact the object is, In other words, the more the material is concentrated near the axis, the smaller the rotational inertia is, right? Okay, that's all we've got for this. Thanks.